We're on slide 36, where you see again this conversion from probabilities via the log to addition here. And that's here, log, so you can add these numbers. And, you know, still we have these ones. These were these random models using the frequencies of the amino acids in the protein world. And this still needs to be set up to be counted. Okay? So basically, you're already using all of this stuff because in the programs you're currently compiling, you score it like this. You add up scores from your BLOSSOM matrix for matches and mismatches. And if there is a gap, you apply some gap penalty, right? So this is the scoring you do, so you use addition already. So basically these numbers are already in log space. Otherwise you would have had to multiply it. Okay, so, but still, as I told you, the real thing I didn't tell you about yet, so that needs to happen. And I'm going to talk about empirical matrices, so matrices that are just taken from the countable world, from reality, from existing sequences. And the two flavors I'm going to talk about for the remainder of this lecture is the PAM matrix. PAM stands for point accepted mutation. More about that in a moment. And BLOSSOM. Yeah. So in my book, I think that this lady, Margaret Dayhoff, is maybe one of the first real bioinformaticians. She wrote a book called The Atlas of Protein Structure. She wrote this in, well, there is even an earlier version, but you know, way before the 80s. I think she started writing in the late 60s, and that just reads fantastically even today. So a lot of stuff, yes, is changing, but some wisdoms are, you know, more eternal than that. So, yeah, she's one of the greats, I think. She died young because of cancer, unfortunately. But she, you know, was the first to use molecular sequences, think about alignment, and set up an evolutionary model in an empirical way using the sequences, and then you know, model all of this. So what was it? The problem was no mathematics to do this, and then she thought of, you know, in this there were already some sequences, a lot less than nowadays, of course, but there were sequences, and she she decided to assemble those from all over the world and start working with them. Make alignments. Were there already programs to align? Perhaps, but could you use them? Well, there were no scoring systems, right? This is the first one. So there is a bit of a problem. So she needed to do alignments by hand. That's, you know, respect, I would say. But I'll get to this. Okay, I'll talk you through the steps in a gloss over way, and then I'm going to really fill you in on how is that calculated using a toy model of very few letters. So here you go. Basically, they have used 71 protein families. Wow, you say that's ridiculous. How can this be? You know, and these sequences were all roughly 80% or more similar. So, again, remember, there were no really tools to do this in a computer. She did it by hand. To get the sequences, not just to download, she had to write on paper using a filling pen, like, dear colleague, I hear you have a sequence of bovine pancreatic inhibitor. Would you guys sending it to me? 2 months later, she got a handwritten sort of letter back with the sequences, maybe 5 errors in it. The guy really wrote down the letters and so on. So that was her sequence database. It's a bit more work than nowadays, right? So it was a fantastic achievement that she was able to assemble 71 independent protein families. She was lucky because these proteins were homologous, but they were pretty similar. 80%, meaning 4 in 5 letters are the same. And then you can do an alignment roughly by hand, right? If you go down to 20% or 30, ooh, you know, a lot of guessing. You run your program. But still it was a lot of work, but she did all of this. She compiled 71 alignments by hand, multiple alignments, so there were 10, 15 sequences in each of these alignments. A bit more than 2, but not so much, so many more than 2. But anyway, okay, what she did as a next step, she was also in phylogeny, she created an evolutionary tree. And what she did do as an extra step, and I'll show you that in the toy model, she reconstructed so-called intermediate sequences. These sequences are, here you see this for example, here's a group, sequence D and E, and this is the common ancestor of these two sequences. And then you have a common ancestor of these common ancestors. And then you have, you know, here is the root, the common ancestor of all of them, right? So, and she reconstructed the sequences. Guesswork, because these sequences obviously were not there, but because the sequences were so similar, this was not so much of a task. If sequences are very different, then this becomes really error prone, but here it was still fine. So, she used this to count, and I'll talk in the toy model how she counted. She used this to count amino acid exchanges. Ah, I see a K staying a K. I see, where do I see something? Where is it? It's all the same stuff, right? Who sees a real, here is one, right? I to T, or T to I. See that? So she took the numbers and filled them in this tally 20 by 20. Just the sheer numbers she took from those elements. Yeah? And she made them symmetrical, this matrix, because she said, okay, change from A to B, in my book is the same as B to A, there's no way of telling what it is. Okay, so then, we might say the next steps is a bit of, a bit of a mathematical jumpery. So she used all kinds of, I'll talk you through this with using the toy model. Basically she said, okay, I'm going to calculate frequencies, I'm going to calculate how much an amino acid tends to change and how much an amino acid, to what extent an amino acid wants to remain the same from these compiled numbers, from these counted numbers. Then she scaled it to a unit of evolutionary time, and then she made a whole series like the matrix after 1 million years, what is the rate of change after 2 million years, what are the changes after 3 million years, and so on, using the model you have already seen a few times already. Okay? So this all happened. So let's go into the toy model. Here you go. I think this is from the day of books. So this is history. This is the real thing. This is how the lady, all conceived it. So here are 4 observed sequences. Toy model, right? So she reconstructed from these two these common ancestral sequences. So the green ones, this is the total the last common ancestor, and this is the ancestor of these two, and this is the ancestor of these two sequences. So this is how she did it. So how is she counting? What happened from this common ancestor to this sequence? A remained A. Do you see that? So that's 1 for AA. What do we see in the second position? A B became a C. Is that counted here? It's counted as CB. So she does the other way around. Okay. G remains G. That's there. And H remains H. Here is the tally of the counts that go into this matrix for this branch. She did this for all the branches. Here are the others. Here are a few. And here are also 4 observations, 4 positions in the alignment. Right? So this is just a line on top without gaps, I told you. And so, you see you can take those. You see this AA, BB, GG. Oh, this is all easy. Is there a mutation here? Yeah, here you see mutations. See that? Here. These ones and that one. Okay, so filled in the matrix. If you do this from this, you can check yourself at home, then you get these numbers in the matrix. Ah, questions, many of them. Hope all the same. Go ahead. Why don't you start asking? You were for a split second with your finger.
In the previous slide, how do you know it's not? I think it was. How do you know it's not the DCGH?
Very, very good. Very clever. I agree. So you say, hey, if you have this, you know the direction. That's your point, right? Is that not your point?
Well,
they have to rephrase it.
I mean, based on those observed sequences, it could have just as easily been DCGH, the inferred sequence, right?
Yeah. I don't know. In her book, not. But that depends on how you do it. Yeah. Well, I could explain backtracking and so on. It probably has to do with the frequencies of these amino acids. That you take a pick, and if one amino acid is more frequent than the other, you tend to pick the one that is the most likely, given the numbers. Okay, A, B. But now you find, I have to choose it. It could be A here or B, but I see that there is twice as much B than A. And then you say, okay, let's put B then.
Okay, so this doesn't come from two single observed sequences, but rather...
No, this is reconstructed. From these two sequences, this is reconstructed. But you're looking over your shoulder to what is happening with all of the data. Backtracking, it's the mathematics, I'm not sure in this course that it comes back, but I can talk about it, but then you have to stay until 5 o'clock. Is that fine? Here, that means, and then do your practical. Another question.
Yeah, so I don't really get it. Which ones are exactly the observed sequences and which ones are...
These are the observed ones. You see here the blue ones.
Yes.
These are the current day sequences.
Okay. Okay,
The rest is reconstructed. This is reconstructed as an ancestral sequence
from
between...
what? Just like from the two, so there's the two of those?
Yeah, so basically you're asking the same question that was asked here. And the answer
I
was...
think it's not clear where
Ah.
the aligned sequences from.
So what's your problem here then? This is clear, so you have a G in position 3 and a G in position 3. What do you expect as a G? You agree? Seems logical, right? The same for the fourth position. H and H here, so that's likely that it's an H
Which
here.
ones are the ones about below the observed sequences? Like there's like aligned sequences, I don't understand that.
These ones you mean?
Yeah.
This. That's not an alignment, it's a tally. Ah, okay. So,
Yeah. Okay.
you take this sequence and you say, okay, this is the common ancestor, so this sequence evolved into this sequence. What happened? That's what you try and do here. What happened? So, you see that an A, the first letter, remained A. There's this one. One AA observation. A to A.
Yeah.
Clear? Say no if it's not clear. Then do it again.
It's clear, but
Okay.
I don't understand how we can be backtracking on something that we've already heard.
No, hold on. Backtracking is that is about how the only question was how do you get to this sequence? Because the choice is made that you have an A in the first position here and a D there. Why do you put an A here and not a D there?
Yeah.
But if you look here, well, I can tell you backtracking means, and here, so you see, so this part of the first question's answer, you see A here, A there. So it's about you reconstruct them such that the mutation rate over the whole tree is minimal. Yeah, and then you put an A here, and that means you have no mutation in the first letter all the way here. How many mutations do you have from A here? One here, no one here, and one there. 2 mutations, correct? Over the whole tree. You see what I'm doing? Do it again. If you have an A here, and we look at all the mutations that happen for the first position in each of those sequences, checking all the branches of the tree, you have no mutation here, no mutation there, no mutation here, 1 mutation here, no mutation here, 1 mutation here. Total is 2. Take the other letter. Suppose you would have put the D here and the D there because it's harder to see, but then you get more mutations. So this is leading to, and that's the assumption for backtracking. That's also an answer to you. That's what it is. But backtracking is just about guessing this ancestral sequences. It's just a way of counting. Let's put it like this. Don't worry if this is all, it's her way of counting and it led to this matrix. Sorry, what is it? Yeah, this one for you. We're on slide 44. But now if you would have checked, I think you see one, here you see AD1. Go back to the figure. Well, you who are quick, they might see 1 AD. Was it? Is there an AD somewhere in the list? Okay, very good. 1. Count the AAs to me, please.
3, 4.
No, I think 4. Okay, let's see what happens. Hey, that's cheating! You make it symmetrical. You put an extra one here, and then it's fair to put an extra one there as well. To keep it in the Yeah, that's what you do. How you massage the data. But this is then the table that you're going to use, the empirical table, the observed world. These are the mutations that happen in the physical world. Well, I think through the glasses of, of this set of sequence of 71 sequence alignments. Of course, much more counts and so on. But that's how it works. Over all of those alignments, you fill the table, and that is what you use, okay? I ask you first one question. To what extent does A likes to stay itself? How would you calculate that? Anybody?
8 times as A would like to change to C, for example?
Well, 8 times A goes to A, right? 1 time A goes to C, and 1 time A goes to D. So how many mutations are there in all? Including the self mutations? 10. So you might say, hey, in 80% of the cases it remains itself, and in 20% of the cases it becomes something else, together 100%. Hey, that's good. Mathematicians like that, right? So what do? You take the row sum or the column sum, whatever, doesn't matter, and then you take. So you normalize using, well, let's say the column sum to do this, yeah? So you say 8 plus 0 plus 1 plus 1 is the column sum, and then you have A divided by that total, and 1 divided by the total for going. So 10% of the cases A goes to C, or C to A, and 10% of the cases D to A or A to D. Yeah? 10% of the cases of A, that is. So that is basically what you calculate here. What I just did, this looks complicated, but that is just what I told you. In a computer, if you want the row sum, you do something like this. You say for the 20, this is about 20 by 20 matrices, so this is just the column sum. The rows go down, I is the row index, so this is the column sum. Yeah? Basically what you say here is, 8 divided by 10 is the same as 1 minus 2 divided by 10, right? 80% is 100% minus 20%. 20% is 100% minus 80%, right? So 1 you can take as the mirror from 1 value. So this is either you look at what is the mutability, well it is 1 minus staying the same, or just calculate it immediately, like here. So this would have been the 1 plus the 1 divided by 10, and this would have been 1 minus 8 divided by 10, is the same thing, okay? So you do this for each amino acid. You take the matrix, and you calculate, for each type, how much, to what extent do they want to stay the same from this matrix, and how do they want to change. You do this by generally this calculation. Now, if you scale these values just to give you a feel, and this is also an old table by Dayhoff using an old database, small database, you get, this is, how much an amino acid wants to mutate as compared to alanine that is put at 100. Okay? So this one wants, 1.5 times faster to go away. But there are also amino acids, other types, that mutate less rapidly. You can see those. What's the slowest changer? Once again, biggest chocolate letter again. What was it? Trip. What's the single letter, guys? Who knows? W. Very good. So W, it's the biggest one on the planet. And then apparently, if you're in a protein, you're big. You know why? In the protein interior you cannot have holes. It's densely packed. So if you have a tryptophan there in the protein core, where they often are, it's a big bulb, and then you change it into something else. You change it into something that is smaller, and you have to fill that space. So the whole thing should accommodate and start moving. And that is not so likely because you have a disruptive change. Yeah? Doesn't happen a lot. That's why you see that tryptophan, this guy, changes the least. Okay. Okay. So another thing is what we wanted from this table. We needed the frequency. Do you remember? For the random model, we needed the frequency of each of those letters. We're going to do this, and the nice thing is, if you use this table that we compiled, if you do this, you just calculate the frequency. So this is just the percentage of that amino acid type J. You can calculate it like this. You take the column sum and you divide it by the total sum over all of the matrix cells. Then you get a frequency of that amino acid type. Yeah? Now, this is just the frequency. And now you could say, and this is what they have also conceived, is, we have this mutatability rate. To what extent does an amino acid wants to go away? You know what? How dramatic is that? So if you have a lot of the amino acid, you get more change. If they all, if you have a lot and that is changing a lot, you get a lot of change. If there is an amino acid type that wants to change a lot, but there are very few of them, then you get less change overall, right? So it relates to as much as the tendency to change, the mutatability, or the mutability, and as well as the frequency of that amino acid type, J and J. Okay? So this is sort of total mutation rate over all amino acids, if you calculate this, taking the sum over the 20 amino acid types. Yeah? So, this is total change. And now Dayhoff, this is sort of an important step she did. She says, you know what, this is counted. We have this protein sequence. How old are these protein sequences? We don't know. How long ago was all of this? You know what, since there is no timestamp on it, I'll make a timestamp. And, my timestamp will be, I find it interesting when all of these changes I will scale to 1%. 1% change. 99% staying the same. I'm going to scale my matrices such that happens. So if you want to do this, this is your mutatability, and then you say, okay, I need some scaling factor over this data to make this score like 1%. And then you solve this for lambda, in this case, the scaling. Yeah? And this defines then an evolutionary period. and that period corresponds to 1% change overall of the amino acid. Yeah? Basically, it starts evolving all the sequences, and the first mutations after the common ancestor, and the second, and you wait until 1% is changed, and you stop. That's the time I'm after here. Okay, so we have a few things now. We have all of these probabilities. So Mij is this probability that we already calculated. You can calculate it like that, mutability. And 1 is minus, 1 minus the other, as we already said. This is just the same as on a few slides back. Yeah? 1 minus, so this was the 8 out of 10 and the 2 out of 10, right? So if you do this, and you scale this, and you calculate this lambda, the scaling factor, and this, if you have that 1%, she calls 1 period. And so that is the PAM1. And this is the matrix with real probabilities, having that data, the real over the 71 families. This is the real data, the real numbers of changing for A. So you can see that an alanine, this is out of 10,000, right? Each of these numbers should be divided by 10,000. So, close to 10,000. And you see that these are the other changes. Are you worried when you see this matrix? This is the result. What number don't you like to see in some of the cells? She didn't have enough data. Can we do? This is so you can't say anything, right? You have that. It's not good, but hey, this was the physical world Dale was living in. She sent all the letters, all the handwritten letters, as many as she could. But this was the data she got. Okay, look at tryptophan. Where is it? Somebody knew the letter. W, what do you see? Is that the largest of the pack? Hopefully, right? You're quick guys, come on. Yes. Is there one? Which is the second? Oh, that's a nasty question. C doesn't like to change. You know why? I told you. Disulfide bridges. They're there very often for a reason. Okay? Okay, so this is the PAM1 matrix, but these are the probabilities. We have to scale them and so on, log and all of this sort of thing we need to do. But what is the model of Dave? She said, all right, this is 1 period. Can I now calculate what happens after 2 periods? Right, in 1 period, you say, okay, we get, you have sequences, they mutate over one period, and now I would like to know what happens after 2 periods. She took an assumption. She said, you know what? The evolutionary rate is not changing. The rate of change remains constant through time. And then it's great, because if you then know what change happens over the first period, you say the same changes happen over the second period. And you can sort of put those after another. So what do you get? Basically, that's what we see here on slide 51. If you have a rate of change over 1 period called PAM1, then PAM2 means the mutations happening over 2 such periods. And just twice the number of changes happen over 2 periods than over a single period. All right? Okay, so what happens? And there are a few assumptions that Dayhoff took, but for now that's not so important. I go to the slide, and that's 53. Here you see what can happen. Now, if you're interested in an A to R change over 2 periods, how can you come from A to R over 2 evolutionary periods? I'll give you a few examples, possibility. In the first period, A remains A. So in the second period, it has to go to R. What also could happen is A goes to N in the first period, and then it should go to R in the second from N, right? So how many possibilities are there to do this? Many. 20 times 20 maybe, roughly. Right? So, if you do this, you add all of those possibilities up. So here you have them all tallied, right? A times the probability of AR, AN times, so all of those. So there are not so many, I think. There are just 20. Right? You go find intermediate letter. So this is always an A, this is always an R. So how many are there in between? Just 20. I was exaggerating with 4. It's 20. Yeah? But now we generalize a bit more. What you could say, what happens after. So, what happens if you have this mutatability matrix, the PAM1, and you say after 2 periods, given that you say the rate of change is the same, you self-multiply PAM1 2 times to get 2 periods. Now you generalize, you say, okay, if I want to know then after k periods, whatever number of these defined periods, you do self-multiply that matrix k times. Alright? So that is what happens. What she does. So basically how this looks, this is, I repeat it here, what I just said. So on slide 57 you see really, if you have this matrix, the PAM1, and you want to know PAM10, 10 periods, or 250 periods, you do 250 self-multiplications of that matrix. With all of the errors in that matrix with zeros. If you start with an error here, mistake, and you multiply that 250 times, what do you think that happens with this error? Because, absolutely. Anyway, that's the physical world in those days. Not enough data. Data problems we always had in bioinformatics early on. And this is now in the end what happens. So here you see that over k periods, and that's why it's not a single matrix Dale calculates, but PAM1, PAM2, 2 cell multiplications first, PAM3, 3 cell multiplications. And the most widely used one is by far PAM250, 250 periods. You want to know how long that roughly is? I'll get to that. How many million years you think? So anyway, this is this matrix I showed you. You self-multiply that a number of times, k times. Then you scale. Here is the log coming in. So now from this moment on you can add the numbers and not multiply them anymore. And here is your pi, and the whole. These are the frequencies. And now we will get to the real values in the end, and that is where is it? They're here. Sorry. So just according if you use this. This is now the final 250 self-multiplications. Yeah? I already am circling one number. So again, positive numbers mean happening more often than you expect. Randomly, positive means more often than expected. 0 indifferent, and negative numbers less often than you randomly expect. Here you see a tryptophan that dearly wants to stay the same. You know, and here at once it says, oh, but going to an arginine from tryptophan, that's positive, right? Well, if you look at these drawings of these amino acids, this one is way different. The arginine is not like, in any sense, like a tryptophan. So what do you think why this is? Data scarcity. Not enough data leads to these type of problems. Right? Question there, yeah.
So the PAM 250 is just the first PAM matrix that we built times.
That is 250 self-multiplications, and that was the one that became popular. They were pushed.
Do we still use this matrix?
It's very funny, I get to that. The answer is less and less. You know what? You know, we know exactly how to I'll tell you something else. It's on the slide later, but this is now the moment, since you ask. We have far more data now. So we could reconstruct a PAM 250 matrix with, 1,000 times the data. People did this. It's called the James Thornton Taylor matrix, GTT. And the GTT matrix, sorry. And well, this problem is solved. You know what people used? Still this one. We're used to it. This is the famous one, right? We're all humans. And so, my program will run differently. I know the patterns like, so this is, humanity takes over. Yes, so all of this can be done better, but this is what happens a lot still. Yeah.
So why 250? Why not 100 or 10?
Because, where was it already on the slide? I've flown a few past. But I'll tell you, it's somewhere definitely, maybe later. Don't know anymore now. One PAM is roughly, ballpark figure, 1 million years. So 250 million years on the scale. Evolution started 4 billion years ago, so we're at 1/16, so totally, that is 250, we were before the hominids, right? There were still bacteria. So most of evolution happened ever since. So this is a matrix that goes back enough in time so that we might be able to align a bacterial sequence with a human sequence. Right? In that sense it's so, but that drives down a very important point, and this is basically here on this slide. Where you see this is the PAM number, and here is the famous one. PAM 250 sort of relates to a sequence identity according to the random model, of 20%. You're in the twilight zone. You're already in very distant sequences, right? You remember for homology how much it was, ballpark figure? Not 20, but 30. You're below homology. This is distant, right? And so, how do you get closer to it? You take, of course, a smaller number of self-multiplications, so that's 200 is less, you see, sequence similarity goes up, at 110 you're already at 60. The question about why PAM 250, Stephen Altschul, the one of the conceivers of BLAST, very clever guy, mathematician, he calculated, let's do information science around these matrices. What is in the information sense the best matrix? And he said, oh, it's clear. PAM 110 is the clear winner. They would hope that the whole world says, oh, Steve, thank you. Now we're going to use this matrix. What happened? Nothing. 250. It's full of errors. Don't say this. That's people get angry at you. You point at important things, If it's not mainstream, you get criticized. You're a terrible person. You shouldn't have said this. They're all upset now. Okay, anyway. Well, this is this is the PAM model. So basically, here is that and is day, all right? Is it 1.5 million? But this is the dream. It's roughly 1 million, and that means PAM 250 is 250 million years. Okay. So here is a summary, but I would like to drive down one more important point to respect about evolution. Well, it's somewhere on the slide, I tell you just like that. PAM 1, how much was that? That was 1% change, right? So we say what happens, the most important measure PAM 250 is 250 such periods. So what percent change is that per site? 250 times 1%. How much is that? It's 2.5. 250%. That means every site under this model is supposed to have changed 2.5 times. Every site. On average. This is evolution. You think, we see a sequence and it's all similar. Behind the screen, there is a hell of a lot of dynamics. Evolution is testing a hell of a lot of stuff. And it doesn't work. It tries again. Right? So, that's the rate of change for PAM 250. 2.5 change per site. I would say respect, for evolution. Okay, so there are a few slides. Here is that table. John Thornton, and so it's John Thornton Taylor, so JTT is the matrix now called. Here in 1992 they did all the work again. Maybe it's time for an update, you might do it. The database is again 100 times larger, if not more. But don't do it because nobody will use your stuff. Although, after all these years, JTT is now used a bit more than PAM 250. So, reality, it's clicking in. There was another matrix that was the best, certainly according to this gentleman, because this gentleman tends to say everything he does is the best there is. Okay, you have these people. Nobody cares. Anyway, let's go to the next one. The one you might want to hear about, right? I can tell you, a hell of a lot simpler, the calculations. So, but what is important for Dayhoff? There is a lot of modeling because the assumptions are taken, and the most important assumption is what happens in the first million years. The same rate of change happens in any period after that of a million years. Yeah, and that's why you can do the self-multiplications. Right? If the rate of change would be different, so evolution ticks with one clock. And this is the old-fashioned model. A uniform evolutionary clock. Who has heard about Stephen Jay Gould? One of the important paleontologists. He's written very many great books. Very worthwhile to read. He came with the thing of punctuated equilibrium. In real evolution, there are all kinds of... The dinosaurs died. Why was that? A meteor hit the planet. So sometimes you have a big thing happening. Half the species are wiped out. A deluge of whatever you have, and a tsunami. All kinds of things happen. So evolution is not something that goes on. It's bang! Wiped out. A lot of stuff happening after that. The planet is heating up. A lot of evolution to withstand that, to adapt. And so this is not real. I told you, mathematics are there to deform reality into something that is tractable, but it's not so real anymore, right? But that's how we do it. Anyway, here is the couples, Stephen Henikoff and Georgia Henikoff. They work together a lot. They're still a couple after all those years, working, spanning everything. It's fantastic. And BLOSSOM stands for the block substitution matrix. And they had a database they called blocks. They left this idea of, they said, you know what, all this stuff like assuming that evolution has the same rate all the time. We're not going to touch this. We're not going to take this assumption. That's very important for our matrix. So they said, let's come up with something that's not having to use this assumption, like Dayoff needs. And they decided to take the rate of change from the data. And for that, they made a database called blocks. And they aligned many sequences using, well, basically using motifs. These were areas that were functionally important. There are motifs, functional motifs. They looked where these motifs were and then said, okay, let's take these blocks of alignment that are important for function. So Darwinian selection is supposed to take place in these regions, so we take those blocks. And then they said, you know what? If we want to calculate sort of near evolution of similar sequences, we take those blocks where the sequences have remained similar. And if we want to say something about more divergent evolution, we include blocks where the sequences vary a lot more, where the letters become more different. So they don't take any assumption, they say we take how much evolution that diverges directly from the data. And that's an important distinction with the PAM approach, okay? So again, this is also a BLOSSOM, but now I need to, it's always confusing. The PAM, the larger the number, the more distant the evolution. And of course, with BLOSSOM, it's different. It's the smaller, the more similar. Because what do? The matrix you are using, I think, in your exercise, in your assignment is BLOSSOM 62. What is that? That means these blocks in the database, these bits of the alignment, blocks are taken that have, where the sequences have at least 62% sequence identity of that block on average. Yeah? And that means the higher that number is, the more similar the sequence is, so the less divergent evolution. Yeah? The smaller, the more distant. Okay? Here you see all of this, so if you read this, you have all of that. Yeah? So let's go for a toy example. No trees anymore, no backtracking, all of these trouble things are gone. They do it using combinatorics. Here you go. This is a bit of alignment they made. They have far more data, of course. It was in 93, this matrix was 92, this matrix was made for the first time. So here you go. You take all of the mutations you observe in each of the columns. Here they are. Column 1, 2, 3, 4, 5. 5 columns here in the alignment. You see that? So, and then the question is, how many AA substitution do we see? How many do we see in the first column? There is one A. How many do you see in the second one? A, and there's an A there. One AA. How many do you see? That's interesting, right? How do you do this? How many A's do you see? It's all A. So what are the mutations you have? A to A, 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 and A to A. And that is the formula for these all combinations. N times N minus 1 divided by 2. And N is 4 here. So 6 mutations, if you do all the combinations. A to A. That's how you calculate it. And 0 and 0. So you do this for all of the 400 different mutations. You take all of those alignments, get all the numbers and put them in a matrix. Yeah? And again, you take them in the mirror image. VA is the same as AV, right? So here is the matrix as a result of this. And again, this 14 you won't find back. That was 7 if you really take the number. Same trick as Dayoff does. You mirror, make the matrix symmetrical by echoing the symmetrical numbers, and you double the diagonal. Yeah? So now you do. So now you start calculating just 2 probabilities, and then you're done. So the observed probability that a mutation occurs between any amino acid I to J is like this. The number in the matrix divided by all 400 matrix cells. Let's you do it straight here. Yeah, this is just adding up all the numbers in the matrix. You take any cell, you divide it by their total, and that gives you a rate of change in the way that the Dayoff couple calculated it. And here is the outcome if you do that. If you add up all the numbers, I think it's 16 in the matrix. So from that matrix that had a 14, look at the matrix. Here, 14 and 8 and 5, you see 2, those kind of numbers you find back here. You see that? But the denominator is 60, that's the whole thing added up. Okay? Then you have this, so this is your observed mutation rate. You have them straight away like this in their scheme. And this is again that same thing that they of did. This is just calculating the frequency of each of the letters, taking the here it's the row sum, but it doesn't matter since the matrices are symmetrical. Take the 1 divided by all the numbers is the frequency of that amino acid. Yeah? And you do this for all 20. So here you have for these 3 types, you have those frequencies. Yeah? Now you're done. That's all. You have this one, you calculated the cell divided by the addition of the 400. This is the frequencies. You take not the 10 log anymore like they have, you take the 2 log, more information theory like. There you go, and these are your numbers. Very simple. And this leads to, and you see the numbers are a bit different here. For the Blossom 62 raw numbers, here they are, all times 1,000, so you have to divide it by 1,000. So you see, this matrix basically is this is less conserved than the day of PAM1 I showed you, but the PAM 250 has far higher off-diagonal elements than this one. This is a more conserved matrix than the PAM 250. But it doesn't matter. Well, it does, but not for explaining this. So, and if you then take this 2 log 2 out of these numbers, you get these. And you scale them, and you see all of these numbers are whole numbers. That's suspicious, right? They interpolated this. In those days, computers were so much faster with integer calculations than floating points. Okay, let's do it. But this is the formula. You see back this one, so the real model divided by the random situation. Eh? This is the old formula you see back here. These are the numbers, and again, which one is the most conserved? Not 17 anymore, but just 11, you see. And then what is the second one? Still see, same patterning. But this one is a more conserved matrix than PAM 250. Okay? Again, this is how you interpret those numbers, positive, 0, and negative. But, and this holds for both, if you want a very high number, how does that happen? Okay, I show you this. How do you get the high number here? How can this become a very large number? I can tell you, Pij becomes very large, or Pi or Pj becomes very small. That means if you have an infrequent amino acid like tryptophan, then this will be small and the number tends to be higher. So if you mutate a lot, you become higher. But if you have a low frequency, the number becomes high too. So this combination in both, but certainly directly in the Blossom matrix happens. Yeah, common amino acids have lower weights, larger frequencies, lower numbers. So this is the combination how you interpret this. Yeah. Okay, so if you want to compare them, PAM versus Blossom, an explicit evolutionary model, single evolutionary clock. This is just empirical. We're not taking any assumptions. We just calculate right from the data. Derived from a small set, 80 to 85% similar, so roughly 15% different. This is more diverse, and you take a selection of the similarity out of the blocks database. Higher PAM means more evolution, and here it goes the other way around. Errors in PAM1 are scaled here. No blowing up of errors here because you take it directly from the data. So this matrix might be a bit more stable, and it's less complicated. Here you see how can you compare the two. Then you calculate a single number called the entropy of a matrix. If you use this, here is the list. So Blossom 62 you're using is roughly equivalent in terms of this score with PAM 160. It goes on. Or PAM 170 in the other end, see? In between 160 and 170. PAM 250 is more like Blossom, whereas Blossom 1, Blossom 40. See? Roughly. So this is how the two series hang together. Yeah? Okay, so think about evolution like this. You see here a wall, the castle wall, right? This is evolution started yesterday. Common ancestors was there yesterday. Now we have two descending sequences. How much change do we have in a day? Nothing. Everything is conserved. So the diagonal is up, and this is 0. And then you get mutations. So what happens? Bricks fall off the wall, right? And they land as off-diagonal elements here. And if you go on for PAM 4000, you just have completely random, so there is no wall left. And PAM 250 has sort of, you know, a little bit of a wall, and the Blossom 62 has a bit more walls too, right? You know, it's less eroded, you might say. Alignment is a, I didn't tell you, but I should maybe, but I'll do it now. You know, if you talk to a philosopher, he says this is not scientific, it's terrible, because alignment, you know, is a circular reasoning. And in science you should never do circular reasoning, it's wrong. And then you say, well, in biology everything that's circular is interesting. You know, feedback, everything is about feedback loops, and that is circular reasoning according to some philosophers. So, but basically, to be able to carry out an alignment, you need a matrix, right? An exchange matrix. Now, how did we now compile the exchange matrix? With alignments. So how could Dayhoff break this cycle? By having these very close sequences, doing the thing by hand. Right? So she bootstrapped alignment, and then she could do this. Yeah? Okay, a few more points maybe. The in practice point, this one I want to show you. This is what you're going to, and then I stop, I think. This is an old paper, 95, but this was a way of checking how can alignments go wrong? How similar, how can we be sure that our alignment is correct? And what did they do? They had alignments where they again knew structure. So they had all kinds of pairwise alignments, and they aligned them according to structure, hope for the best, and they took that as the standard of truth. But an alignment that was based upon structure. Looking at 3D structures, comparing and say, oh, this is equivalent, so put that on top. So you had alignments that were supposed to be true here, this side. And this is, if they started aligning, they said, okay, we take two sequences, and suppose they're 50% difference after alignment. We have various alignment methods. We take that alignment method that gives you the best score, the best possible one for that pair. And then we look, if you compare that alignment, the best one possible, to the reality, this is where you are. So what do you see? Is that there is a superlinear degree of errors you make, you know, all the way until 50% there is no problem, you're close to 100% correct, right? But look here, the 30%, where are we? So this is here the figure. So you impose already 20% error or more in your alignment. And if you want to be really, you know, here is the twilight zone, yeah? Now we're trying to solve it here in alignments between sequences of 15% to 20. Your error rate is 70% or more, according to this. So we make serious errors, right? So remember that. Even your program, you won't believe me, is making alignment errors, biological errors. Even if it runs perfectly, yeah? You will get 10 points from us, but that's because of the models, of the matrix, the way we align, of the shortcuts and of the simplifications we take and the assumptions to be able to calculate an alignment in the first place. So here are some, they're going to show all these points. Yeah, you're off, and I'm up slide 85, which is the last one of the pack. Many slides, right? Many repetitions. Yeah.